Hello and welcome to part 2 of lecture 23. I'm just going to go over a couple of medium length examples, and that will be the entirety of this video. So we're going to continue to talk about work and power for rotational systems. In example 2, we have a thread wound 4 times around a pulley with a diameter of 30 centimeters and a mass of 5 kilograms. We're taking the pulley to be a cylinder, so it has a moment of inertia of 1/2 mr squared, right there. And we want to unwind the thread by pulling it for 1 second. Okay, and what minimum constant force do we need to apply to the thread? What is the average power expenditure of pulling this thread? And what is the instantaneous power expenditure at 1 second after the pulling has begun? All right, so I got a whole page to solve this, although I won't need all the space. Okay, so let's set this up. I think a picture is not a bad idea, so we can know what we're thinking about. So let's draw our cylinder, something like that. All right, and we know we have thread wound around it. That means there's going to be a force that's going to be exerted from the thread. So here we have the thread kind of coming off the end, and then I'll draw the force. Like so. All right, something like that. Okay, so that is the force that we're interested in. That's going to be our minimum constant force. We'll just call this external force. That's what we're going to be applying via the thread to our pulley here. All right, and then the pulley has a radius, because of course it has a center. So right here, and we'll give it a radius, and that is r. All right. We know its diameter is 30 centimeters, so its radius will be half that. Okay, so in order to set this up, of course, we're going to need torque equation. It's rotational, and there's a force involved, so torque is the natural thing to think of. And the go-to equation for torque is net torque equals I alpha, and then to parse what net torque is. In this case, net torque is going to be the torque created by the single external pulling force. So it's just torque net equals I alpha. That's just Newton's second law. Okay, and then what is torque net? Well, torque net is just going to be F times R times sine of 90 degrees, because there's a 90-degree angle between the radius and the external force. And that's true of anytime you have something wound. Okay, so anytime there's a string or a pulley system, it's always going to be 90 degrees between the tension force or the pulling force, whatever it may be, and the radius, because that's the way the string comes off. It comes off to make a right angle, right? Kind of that contact point. So then it's force external times radius equals I, which we know is 1/2 mr squared, times alpha. Okay? Now, do we know now alpha? Well, not yet, but we're given enough information to find it, because we know that the pulley is going to start from rest, and we want to unwind it by pulling on it for 1 second. Okay? So that means we need to have a case where we have a final displacement, and then we want, and let's see, diameter of the mass, 4 times, okay? So we know it's wound around 4 times, and we know we need to completely cover that angular displacement for circumferences in, well, 1 second, okay? So using kinematics, we'll find alpha. Okay, so what does that look like? Well, that's just going to be our theta final equals our theta initial plus omega naught times t, and then plus 1/2 alpha t squared. Okay, so it starts from rest, so we have a 0 there. Our initial position is it's not unwound at all, so it's also 0. And then our final is going to be 4 times 2 pi, all right, because that's 4 complete windings. So 4 times 2 pi replaces our final angular location or displacement, and then just 1/2 alpha, and then times 1 second squared. Okay, and so then when I go ahead and solve for alpha, I'm just going to get, well, if you think about it, it's going to be, because here I have 8 pi, and then I get, 16 pi, and then I divide by t squared. In this case, it's just 1 second. So I'm just going to get a alpha of 16 pi radians per second squared. So 16 pi radians per second squared. Okay? All right, so then I can go ahead and plug that in and then just solve for r. Okay, so what will that look like? So then my minimum external force to pull this off, or really the perfect force to pull this off, because otherwise it would unwind too fast, and we know we want it to unwind exactly in 1 second, is then just going to be my r 1/2 m, and we divide it by one of the r's, so that's going to cancel out just to be a single r. And then we'll multiply by our 16 pi radians per second squared. I'll plug in some more numbers here because we know that our mass is 5 kilograms. Okay, its inertia matters. Okay, and we know its radius is 15 centimeters. Okay, and then we'll just get our 16 pi and our radians per second squared. All right, so once we plug that all in, we end up with 18.9 newtons. All right, so that is our force. Anything about power? No. Okay, that was just a strictly torque and practice with Newton's second law in rotational form type of problem. But that's just part A. So now let's get into part B, where we are asked a question about average power. Okay, so average power, by definition, is just going to be our force, basically, or our torque over time. Okay, so we just have our torque over time, okay? And our torque is just going to be basically the force, the radius, and that's it. Yep, it's just overthinking it. But yep, so it's just going to be so that was just going to be force times radius, because that of course is our torque. And let's give a subscript here, make sure we're all talking about the same torque. All right, and here, yeah, torque net, which is just force external. Good, okay. All right, and good. And that's still going to be divided by the time, okay? We know what the time is, right? And we know that our torque is just going to be, let's see, what am I forgetting here? Oh, that's right. I need theta. Okay, so let's put that in there. So it makes a little more space here. So it's going to be torque net times, well, here we're asked for a specific torque, so let's call it torque external, the one that matches up the force, the pulling force, times theta all over T. And if you want to know what we're referring to, let's take a look at the equations, right? All I'm writing here is that power is change in work over change in time, and the work is simply equal to, because it's constant torque, the work is equal to tau times delta theta, okay? All right. In this case, I'm just calling it theta because it's really just theta final because our theta initial is 0. There we go. I knew something was missing. Okay, and so then what that looks like is, so now we can write our torque. Okay, have I expressed the torque exactly? No, but we know what it's going to be. It's just going to be F external times radius. So it's just going to be F external times radius, and then times theta final, okay, which we know to be just 4 times 2 pi. Okay, and then we'll just divide that all by our time, which was stipulated to be 1 second. All right, now we are set. Let's plug in our numbers. Go ahead and do that down here. All right, so now 18.9. See, now we're using that force that we solved for in part A. Okay, so if I just asked part B, you would have had to find the force and had to know that that's something that you needed. Okay, well, and ultimately you could have thought of it as finding the torque, but ultimately you needed to find something that was keeping the system going. Okay, that met the criteria, the particular acceleration, right? That was expressed in a roundabout way, because I asked for displacement over time, but that's just a roundabout way of asking for an acceleration. And then we got our radius, and then our 4 times 2 pi. That's our 4 complete winds. It's just four revolutions. All right, and then it's all going to be over 1 second, which will change the answer numerically. All right, and that gives us 71.3 watts. So that's our average power. Obviously, that's not going to be constant, right? It's not going to be exerting that much power, say, when it first starts, because if you think about it, at the very beginning, sure, yeah, the torque was always the same. The torque is constant for this particular system, but the displacement isn't, right? And so when the system first starts, there's actually no power being expended by the force. And the longer you pull with the force, the greater and greater power that it extends, okay? Because the displacement gets larger and larger. In fact, let's put that into practice, right? It's really kind of hone in on the idea that the power is going to be growing, okay? And the power will be growing linearly for a constant acceleration because the power is proportional to the velocity, in this case, the angular velocity. Okay, so what does that look like? Well, we saw the equation back in the key equations in the last video and also just recently when I flipped back. And that's just going to be, oh, I wrote tau, but I meant P. That's just going to be instantaneous power, so no bar, right? Because that bar represents average. That's just going to equal tau times omega. And that's just going to be, and a subscript there, so that'll be force external times the radius, and then times the displacement, okay? Oh, I'm sorry, times the angular velocity. Let's take two things at once, okay? And then what is the angular velocity? Well, right, what are we looking for here? I asked for it in part C at that 1 second, right? Well, at the 1 second, that would just be, well, alpha, okay, which we know, times t. Ah, so that means we could actually write it like this, okay, times radius times alpha t, okay? And that's just from the fact that the kinematic equation, right, tells us that omega, as an omega final, equals omega naught plus alpha times t, okay? And if I'm being any way consistent, I could call it omega initial, right? Okay, and in fact, let's make it final because it is after 1 second. That was our final time after all, okay? But anyway, the key thing is that this is one of our really familiar kinematic equations, maybe less familiar in omega alpha form, but something we saw a lot when it was x and a, or y and a for that matter. And it's simply that, right? It's simply the linear growth of velocity with constant acceleration. Okay, and so then we can go ahead and find that value. I was used the space since I had it, but I could have written much smaller, but hey, we filled up the whole page, see? So let's plug in our external force. So we got our 18.9 newtons. We got our radius. We know our alpha, right? That was up above, was 16 pi. All right, that's radians per second squared. And we know our time was 1 second. All right, looks good. So when we plug that all in, we get a power output of 142 watts. All right. So these are rounded, right, to 3 sig figs. But there is something to notice here, that 142 is exactly twice the average. And that's because of the constant acceleration. It wouldn't be true if it was a non-constant acceleration system. But here, in this particular constant acceleration system, what's actually happening is at the very beginning, right, when the velocity is 0, when the system is just starting for motion, the power output of the force is 0, okay? Because it hasn't done any work yet, right? And you can't have power unless you've done work. Work requires displacement. If it hasn't displaced anything, no work, right? No power. But then as it grows, right, as the displacement grows parabolically, well, then it turns out then the power grows linearly with the velocity, of course, as I said. And so then you end up with a result that the average is just halfway in between the initial 0 value and the final max value. Because that right there is actually the maximum power that will be outputted within that whole second of pulling. All right. All right, hopefully that's interesting and straightforward. All right, so we got one other example. I'm going to leave example 4 and 5 for practice. So there's further practice for you all. But 3 is different enough that we definitely want to take a look at it. And what's going on with 3, right? What's the difference with 3? Well, the difference with 3 is that it is a torsional system, okay? Now, torsion is not something I spend a lot of time on. However, there are torsional examples that are included in the problems in the back of the chapter for chapter 10. The book doesn't kind of call a lot of attention to it. Some other books do. And although I didn't assign any in the homework, they could show up as adaptive follow-ups. And I do want to make sure that it's something we see how to do at a basic level, okay? And so in example 3, it's just that. Okay, so in an ideal torsional spring, we can have a torque that is linearly dependent on angular displacement. So it's just like a spring, right? So it's just like Hooke's law, F equals, kx, but instead of F, it's tau because it's a torque, and instead of x, it's an angular displacement, it's theta. So we can really think of this equation, let me highlight it, this equation right here as torsional Hooke's law, okay? Let's make a note of that. So tau equals k theta is Hooke's law for torsional springs. And of course, a torsional spring is a fancy word for a twisting spring, right? And if you think about it, a lot of springs actually are, a lot of everyday springs. Not all springs are just kind of translational, right? All right, for a torsional spring. Okay, so again, trying to leverage everything that you kind of have learned and learned to expect about Hooke's law, right? It's the whole idea, the force grows with displacement. Here, the torque grows with displacement. Here, the displacement is rotational instead of actual distance. Okay. In this case, we have our spring constant. Okay. So in this particular example, our spring constant is kappa, right? Because we're doing Greek letters here, so instead of K, it's kappa. Okay. And kappa is going to be 450 Newton meters, right? Different units for the spring constant here. In fact, they're the same units as torque because theta is unitless. All right, but that makes sense. Okay, and that's just due to the material properties of the spring, its geometry and what it's made out of. Okay, and so then how are we going to actually find what we were asked? We were asked how much external work is done to twist the spring. Okay, so the idea is that we have the work of rotation, okay, which would be like the work of twist as you think of it, and that's going to be in the general sense equal to theta initial to theta final of tau d theta. Now, why am I writing it that way? I'm writing it that way because, well, tau is very much a function of theta. That's the whole thing about springs. Just like when we derive the elastic energy stored in the spring, we got the 1/2 kx squared. That's because of the integral. That's because we use the general form of translational work. Okay, so here we really do have to integrate. All right, and then we're going to be going, all right, this is when we're going 1/4 rotation. Notice that's mentioned. Well, 1/4 rotation in radians is going to be pi over 2, right? Because a full rotation is 2 pi. So we'll go from 0 to pi over 2 radians. Okay. Now we'll put in our torque, which is just going to be kappa theta. Okay. And then we have our d theta. All right. So this is obviously going to be a very easy integral. It's just going to become 1/2 kappa squared. Okay. And then we're going to go ahead and integrate. Excuse me, it's not kappa squared, theta squared. All right, where's the right? Not integrating over kappa. Kappa is constant, long to the right. Okay. Then I have to evaluate on my limits of integration. So it's going to be from 0 to pi over 2. So that means that in this particular case, the work that was done is just going to be 1/2 kappa times pi over 2 squared. All right. Plug in some numbers here. So we got 1/2 times 450 Newton meters times pi over 2 squared. All right, looks good. So that ends up giving us a value in Newton meters, or joules for that matter. Put in joules, right? Because I like to just as often express work in terms of joules as Newton meters. I'm not a stickler for one or the other. But it's 555. Right? That's how much energy, of course, because work is energy. That's how much energy it would take to twist this particular spring, to load it, right? Load it up. All right, so that includes our second example to get some more practice with work and power of rotational systems.